This was yesterday. Who told you that we are still recording?
So you just form off of it.
I'm going to write to my, well, none of my friends were thinking content. Oh, yeah, that is. Oh, sorry. Oh, you're here? No.
No, I just thought like
Actually, I was thinking,
I think today we are fortunate to have
because you're going to stand here.
we're fortunate to have a last minute visitor. Adam Bowman visiting us from Perimeter, who has generously agreed to give us a discussion of dynamical edge models and entanglement, the Maxwell theory. Thanks, Lloyd.
Thanks. Yeah, I'm glad to. Oh, yeah, you figured it out already, but I've got a stutter, so thanks for bearing with me in advance. But yeah, I'm pretty excited to be able to share this. I want to just make sure that that works. Yeah. The title says dynamical edge modes in Maxwell theory. This is from a paper back in March. But I'm finishing up a paper now, generalizing it to P-form gauge theory, where pretty much all the results go through just the same. But it's kind of cool because Maxwell theory is conformal in 4 dimensions, whereas P-form theory is conformal in D-2/2 dimensions. So we get an infinite family of CFT special cases to play with and get a little more control with that generalization. And then, of course, we're also very interested in generalizing it to gravity. So we're making slow progress on linearized gravity as well. Okay, so what are they? These edge modes. I'll say a little bit about that, and then a little bit about entanglement and standard path integral approaches to it and problems with that approach. Then give an alternative approach to computing entanglement that works for both scalars and gauge theories just the same. So sort of a unified paradigm. Yeah, and then I'll get into the specifics of how we managed to do it for Maxwell theory. Yeah, we put a boundary condition, and then the phase space factorizes into bulk and edge parts, and the Hamiltonian splits as well. So that means the partition function factorizes, and then the edge part of the partition function will resolve some mysteries in the literature for if people have computed entanglement gauge theory and gotten conflicting answers. Right. This will be for 3 games. Yes. Yeah. Yeah. So in gauge theory, edge modes are degrees of freedom associated with large gauge transformations. So if you have your theory and you're studying it on some spatially finite region, then the gauge transformations that are not supported on the boundary, those are going to be redundancies. They correspond to symplectically trivial directions. They get quotiented out of phase space, but depending on your boundary condition, the gauge transformations that are supported on the boundary are physical, and they also end up being symplectically conjugate to the electric flux through the boundary. It's closely analogous to the asymptotic symmetry story for if you study gauge theory or gravity on a spatially infinite region, then the gauge transformations that don't die off very fast can be physical, and those are asymptotic symmetries, and they're related to some sense of Goldstone mode. That the asymptotic symmetry is spontaneously broken, and it has a conjugate partner, a massless mode. Yeah. So for the finite manifold case, the edge mode kinematics were partially understood from different sides, from these two great papers in 2015 and 2016, but for both those cases, the dynamics for these degrees of freedom were basically not studied. Edge modes play a important role in horizon physics and entanglement, and probably a lot more things too. But the slides I have here concentrate mostly on the entanglement part of the story. Correct. Yeah. So a review of entanglement. Let's start on that. So you're studying the theory. It has some Cauchy slice sigma. You can split it into some subregion A and then some complement A bar, and then you form the density matrix for the theory on A, which is to say you forget about the complementary degrees of freedom. You trace them out, and then the entanglement entropy of your state psi on the region A is defined as the von Neumann entropy of that density matrix, the negative trace rho log rho. And this setup here assumes a Hilbert space factorization for your region versus its complement, and that's never actually true, but for scalar theories, for example, the problems with factorization are just UV problems. So you're almost always going to use some UV regulator anyway, and most of them solve this problem for you. So historically, people got away with just ignoring the fact that the Hilbert space doesn't factorize. And it's sort of intuitive that there will be UV obstructions to the factorization, because you have lots of UV modes piling up near the interface. Can also be understood as that if you try to treat the two sides independently, generically there will be a discontinuity associated with diverging energy. But yeah, many UV regulators solve the problem. But gauge theories have IR obstructions to factorization of the Hilbert space as well. Related to constraints. If you treat the two sides separately, you'll generically violate one of your constraints. That's a problem no matter what the energy scale is. And it's also sort of intuitive that like gauge theories have extended objects like Wilson lines. So if you have one that's crossing the interface, then you have to be careful about that. Cutting it open might give you new degrees of freedom. But both obstructions to Hilbert space factorization, the IR and UV, can be handled simultaneously with the approach of shrinkability. Right, and I'll review the path integral approach, but before saying what I really mean by shrinkability. Right, to compute the entanglement with the path integral, you start off with Cauchy slice, and for concreteness, let's work in Minkowski here, and then I'm going to be splitting into left and right Rendler patches. Yeah, so split it into A and A bar, the complement, and you've got the interface dA, and the global vacuum state can be prepared with the Euclidean path integral on the lower half space. So your wave functional of some configuration is defined as using that configuration to place a boundary condition on this slice, and then you just do the Euclidean path integral for negative imaginary time. And the corresponding density matrix, well, it's just preparing that same state twice, and one is a bra, one is a ket. So I've written one in the lower half plane, one with the upper half plane. Yeah, and then tracing over the complementary region just corresponds to sewing together the path integral for that part. But yeah, but something weird is happening at the origin, and depending on what you calculate, that's usually going to cause some singularities, some extra divergences. So you really should regulate it somehow, and one way to regulate it is to cut out some small disk around the origin, and then place some boundary condition on the circle, the little circle boundary there. And as long as you choose a local boundary condition for that little red circle, then the like rays emanating out radially from it should have a well-defined Hilbert space on them, which allows you to talk about like a state on one of these lines evolving angularly by 360 degrees and coming around back to where it started. Right. Yeah, and then back in the Lorentzian picture, cutting out that little Euclidean disk, Wick rotates to taking your horizon and putting a brick wall boundary near it. So some brick wall that hugs the horizon, and once again, as soon as you introduce a boundary, now you have to choose some boundary condition to get a well-defined theory.
So sorry, in this picture, you're computing the entanglement entropy of the vacuum, the ground state. I guess.
Yeah.
Is there a way to study other states?
Mm-hmm.
With this?
Yeah. So for any state, the definition of the entanglement in terms of the finite entropy is just the same. But for this path integral argument, you're kind of limited to states that you can prepare with the path integral, which I guess if you allow insertions, that's still pretty much all states. Yeah, so some of them would have less simple geometry, and then maybe the subsequent tricks would be less tractable. But but pretty much any excited state, you should be able to prepare with the path integral and use the same kind of replica.
But you'll use the fact that the entanglement Hamiltonian is still beta, or
Yes. The modular Hamiltonian is generically a non-local operator, but when you're studying like static geometry, for example, like boosts and Rendler, they preserve the geometry. Yeah, then the modular Hamiltonian just coincides with the static Hamiltonian. Yeah, for that killing vector. Right. So back to Euclidean signature. Yeah, we cut out this little disk, placed some boundary condition, And now manifestly and without extra singularities. Like you still have to do some usual regularization, but there's no extra complication associated with the origin now. Yeah, the trace of ket bra is just e to the minus 2 pi Rindler Hamiltonian, which is the same as the Euclidean signature angular generator.
Is this answer dependent of the boundary conditions that you place at that disk?
Good. Yeah. The answer does depend on the choice of boundary condition, and there are some bad choices, and we'll call the boundary conditions that recover the plane with no hole shrinkable boundary conditions. Yeah. You choose some boundary condition for like generally speaking, when you take the limit as the hole goes to 0 radius, your choice of boundary condition will result in some defect being at the origin once you take the limit of it being small, and we want to find a boundary condition that shrinks to the identity defect. So this path integral here really does correspond to e to the minus 2 pi Rindler generator, and then you normalize that so that it has unit trace to define the density matrix, and then you can compute trace row of that density matrix. Yeah, but the question is whether that von Neumann entropy for that density matrix is equal to the entanglement we were originally trying to compute. And the conjecture is that as long as you choose a shrinkable boundary condition, then the von Neumann entropy should be the entanglement you wanted. Yeah. So yeah, we got a picture of the plane with a hole here. Yeah, when you shrink it down, you expect some defect, and shrinkable is it's the identity defect. And that applies to the partition function and all correlators as well. But in practice, sometimes you can only check the partition function, which is still decently strong evidence of that it is a shrinkable boundary condition. Yeah, and spoiler, the key for Maxwell theory will be that we find a boundary condition that includes the edge modes, and that ends up being shrinkable. Right. So yes, some context or motivation for this is that in 4 dimensions, Maxwell theory is conformal, and there's the famous Cassini-Wharton-Myers paper showing that in CFTs the entanglement going across a sphere in flat space, the universal log coefficient of that entanglement is given by the type A trace anomaly coefficient for the CFT. So it's a relatively reliable way to figure out the entanglement, for 4D Maxwell, that tells you that the coefficient is supposed to be negative 31 over 45. But some people, for example, Dowker in 2010 tried to compute the entanglement for Maxwell theory and found instead negative 16 over 45. And the
Almost.
yeah, 1/32 off. Yeah, and the difference between those two is 1/3, which happens to be the entanglement of a 2D scalar, which is also conformal. So it's very suggestive that that somehow if you could find a 2D scalar within 4D Maxwell, you might solve the problem. Yeah. And because of that, people were guessing fairly quickly that maybe the gauge parameter can somehow be that degree of freedom that solves the problem. But prior to our paper, no one had fully put it together. Yeah, and then there's also further motivation in general dimensions. There's a more recent paper, 150-page paper from people at Columbia in 2020 that they computed sphere partition functions of various theories, and one of their calculations was a sphere partition function, and their other calculation was based on the de Sitter static patch, which Wick rotates to the sphere. So that they expected to be able to do a Lorentzian calculation on the static patch and find agreement with the Euclidean sphere calculation. And they found that for scalars and spin half. But for gauge theory, they were finding this systematic discrepancy where the d-dimensional partition functions always differed by a d-2 sphere scalar partition function. So that's consistent with the evidence from the previous slide that you're looking for a codimension 2 scalar somehow. Oh yeah, and also interestingly, you're actually looking for a ghost scalar. You're looking for 1 over z scalar of sd-2, which is also consistent with, if you paid attention to the signs on the last slide, +1/3 versus -1/3. Right. Yeah. So back to our setup. We took Maxwell. We introduced a brick wall, or in the Euclidean signature, we cut out a hole. We have to place some boundary condition, and we suspect that it's going to be that the gauge parameter is going to be important. So we want to allow these boundary supported gauge transformations. The symplectic form for Maxwell theory is just delta A wedge star delta F, which you could also write as just spatial components of the gauge field contracted with the electric field. Right, yeah, and plugging in a gauge transformation to the symplectic form, you can see that so a gauge transformation with gauge parameter lambda. If you plug into the symplectic form, it reduces to a boundary term, which is a lambda weighted integral of the electric flux through the boundary. So when your gauge transformation is not supported on the boundary, that's going to be 0 always. But if it is supported on the boundary, then it has hope of being symplectically non-trivial. Yeah, so we would like a boundary condition that allows both non-zero boundary gauge parameter and non-zero electric flux through the boundary. But both of the standard boundary conditions for Maxwell theory don't do that. So, for example, the electrically conducting boundary condition, you set the gauge field to 0 on the boundary, which basically kills the gauge parameter too. So that doesn't work. And then the magnetically conducting boundary conditions sets some field strength components to 0 on the boundary, but that in particular kills the electric flux through the boundary. So neither of those will allow the symplectic part that we want. But we introduced a new boundary condition that we call the dynamical edge mode boundary condition, where it's basically the magnetically conducting condition for the spatial components and the electrically conducting condition for the time component. And it still sets some field strength components to 0, but it does not kill the electric field. And it sets the time component of the gauge field to 0, but you're not actually, you don't end up losing much from that because it's already possible to impose temporal gauge. Which is to say, like you already could have gauged that away. So setting it to 0 as part of the boundary condition, you're not actually like losing any degrees of freedom. Yeah, so this boundary addition keeps all of the edge modes, and it turns out to be a strict augmentation of the magnetically conducting one. It has all of the magnetically conducting degrees of freedom plus the edge modes. Yeah, so we show in our paper how to parameterize the degrees of freedom in terms of, we use a tilde for the bulk degrees of freedom, the ones corresponding to that magnetically conducting boundary condition. And then the edge degrees of freedom can be parameterized as gradients of scalars. So as soon as you see that, you're thinking that they're going to be boundary terms. And yeah, that does happen. So just plugging in that parameterization to the symplectic form, you end up with separate terms where the tilde parts are integrated over the bulk region, which I unfortunately called A. And then the scalars alpha and beta, you end up with just a boundary term for those. And then the gradient of beta is the electric field, so I switched back to writing E in the final expression there. Right. Yeah, and some similar expressions show up in papers sometimes where a symplectic form is written as a boundary term plus a bulk term, but in lots of those expressions, the same degree of freedom is showing up in both integrals, whereas for this case, the bulk integral does not at all use alpha and beta, and the boundary integral does not at all use the tilde parts. So this actually does indicate a split in the symplectic form and a factorization of base space.
When you're doing transassignments, three dimensions,
Mhm.
the boundary condition you eventually pick there. Is that essentially the same
Mhm.
story?
So for turn assignments, you can vary the action, and then you get some on-shell boundary term, and then for it to be variationally well defined, which is closely related to being like symplectically well defined. You want to set that boundary term to 0, and there are two natural options. One of them is like set the spatial component of the gauge field to 0 on the boundary, and the other one is set the time component to 0. Yeah, and it's similar to here. One setting the time component to 0 gives you a rich edge degrees of freedom, and if you chose setting the spatial component to 0, you'd get like nothing. It would kill all of that, and I think it's not talked about as much for that reason. Right, so we can take that same parameterization and plug it into the Hamiltonian, and once again, it splits into bulk and boundary terms that have no involvement with each other. But the boundary term is kind of strange. So I could have written the boundary term here as beta times E normal. Where remember, E normal is the normal derivative of beta. But I chose instead to write it fully in terms of E, because E showed up more nicely within the symplectic form. Like the symplectic form is just diagonalized with a unit on brackets when I use E. Yeah, but if I do that, then I get this weird kinetic term for this edge Hamiltonian. So I called this operator K. It's basically like the effect of taking a normal derivative on a harmonic function. So it's actually, it can actually be defined intrinsically in terms of boundary data. You can think of it as the Dirichlet to Neumann operator. Like when you have a harmonic function on some region, you can specify a solution with Dirichlet data or Neumann data. So if you start off specifying with Dirichlet data, then it's a well-defined question to ask, what's the corresponding Neumann data? So you can define this operator K like that, and You can also write it a little more explicitly in terms of Green's functions, but yeah. So it's generically some strange non-local operator. It's pseudo differential rather than differential. But we showed that in the horizon limit, like the limit of your brick wall hugging your horizon very closely, then this operator simplifies to a multiple of the Laplacian on your boundary of your Cauchy space. Where epsilon is the distance between the brick wall and the bifurcation part of the horizon. So we can plug that in and start computing the partition function, seeing what the edge contribution is to it. The phase space factorizes, so the Hilbert space will, the Hamiltonian splits, so the partition function will factorize as well. And we can just very directly write them as traces. It's a Lorentzian calculation. Right, the bulk piece is just for what you would have gotten from the magnetically conducting boundary conditions. So we're going to just focus on the new edge part. And So I'm very happy to go into detail, but there are actually lots of details swept under the rug in this equation. So I'll just say for now that you take this trace, you do get something proportional to the root determinant of this operator K, which is then proportional to the root determinant of the Laplacian on this codimension 2 surface. And then the determinant with a plus half is the reciprocal of the partition function of the codimension 2 scalar. So the intermediate terms have a bunch of extra factors, but the final term really is exactly 1 over z scalar. So we computed our z edge, found that it is 1 over z scalar, which solves those discrepancies in the literature that I mentioned before as motivation. Is that the end? Okay. I'll stop there. Questions?
So it's gauge theory that it's the fact that you had large gauge transformations, that essential source of the discrepancy. But if you had a scalar that was periodic in 4 dimensions, this is dual formulation in terms of a B field that would also have large gauge transformations.
Mm-hmm.
In that case, would you have gotten 0, or I guess the question is there a difference between a periodic scale like an axial and then a dimensional scalar, or would it be actually the same?
Right. The fundamental charge sets the scalar's target radius for this case.
So this case is okay. So in this case, it's pure with the difficulties.
Yeah.
It's not rational. It doesn't feel rational.
No. So one of our other follow-ups is trying to understand in what sense scalars might have some sort of degenerate sense of edge modes. So we don't have great headway on that, but our P-form results do apply to P equals 0. So that's already very suggestive that it should work in some sense.
Yeah, because it feels like you should have similar. It should have been a similar story.
Yeah.
So just to understand which part of the answer is kind of, robust to. So let's say you added some perturbation on top of Maxwell, relevant in this correction, and you wanted to kind of, study the leading corrections of these things. So presumably it's a sign definite correction to the total entanglement entropy.
Yeah.
But do you think maybe your 0 mode thing is protected? Is there a sense of separation in general? speculate.
Mostly I can't, it's a good question, definitely, but, the paper that comes to mind is that, there's a Cassini and Friends paper where they're motivated by some of the same discrepancies in the literature, but they use very different tools and they conclude that like pure Maxwell is actually a different theory from the low energy limit of like massive QED, which sounds a little strange to me. And they believe that the low energy limit of massive QED like it has this extra 1/3 that resolves the discrepancy, but they believe that pure Maxwell somehow would not have it and just like doesn't match the CFT answer. Yeah, so it's probably related to.
There's some technical reason for Maxwell is not a CFT. It's scalar variant, but it's something that should be a primary, not a primary. Before you misremember.
Yeah. So it's genuinely a CFT in 4 dimensions, but if you go to dimensions other than 4, then
So 4 is good. Yeah. Okay.
So your calculation doesn't really use conformal invariance, but I guess the motivation, the fact that when you have conformal invariance, you know, this
Right.
relation between entanglement and the A.
Right. Yeah. So our well the phase-based results we did for a totally general manifold, but the shrinkability or like the edge partition function result was for a static manifold, a spatially finite boundary. So technically speaking, that doesn't include, say, like a ball in flat space, like the causal domain of a ball in flat space. But we our results do directly compute like the entanglement of the static patch of de Sitter compared to global de Sitter, and in the conformal case, we can map that back to flat space, and to talk about the standard CFT quantity people are interested in.
Did you try the same computation for the 6-dimensional chiral tensor?
No.
I mean, that is a CFT also, and that's a case that would reduce on the 2 torus to this. But there should be a completely analogous story, except you have to deal with the chirality condition of the tensor to determine the boundary condition. So you can
You can do the people.
people non-chiral.
Right.
Yeah. So the question is it that's a good question because it's metric dependent when you cut. So maybe it will cut it fine for the people. Any other questions? Well, Adam is around all day today, so if you want to chat, just come find him either down here or in my office. Let's thank Adam again.
But they are seen as it's not unusual. It's